Hello, how are you guys? There we go. Okay, a little closer maybe here. Here we go. Hi, Carlotta, Rhea, Ada, Aaron. Okay, let me just get you guys checked off here. Aaron is here. Carlotta is here. Ada is here. Louisa is here. Samuel is here. Lars. Eva. Lars. Raske. Friedrich. Martens. Rea Tober. Marvin Lucas ist hier. Vicky Waldrop ist hier. Becky ist hier. Okay, good. Carly, Lars, Aaron, Carly, Samuel, Carly, and then, okay. Okay, hi. Hope you guys are well, enjoying the sunshine. Not too much, but you hope you're getting out to go for a run or go for a long walk to get some exercise going. Remember to stay fit. Don't just stay at home and lay around or, all that stuff. Gavin is here. Okay. Good. Okay, I'm going to just go through the people that I think are not here. And if you are, just put in a hi in the chat. Natasha, Izzy, Johannes, Rafi, Macy, Lena, Emma, Ella, Philip. Those are not here as far as I can tell. So if you do show up, post that you're here. 4, 6, 9, 10, 13 people who I got checked off. We got 14 in the stream. So maybe either somebody's lurking or we've got somebody who didn't put hi in there. Alrighty, we'll check back in later. But let's get going. I've given you guys an assignment. Whoa, shoot. Hey, stay here, computer. Okay. All right. Stay. Good boy. Good. Okay. I've given you an assignment for a lab. It is virtual. Hi, Izzy. It is not actually, obviously. Well, you could. Well, anyway, I'm getting distracted. I mean, I'll think about if I can set up a lab that you guys actually do at home. There are some things we could do, but this lab you guys will complete online with the PhET simulation, PhET, that I sent you guys. I posted the assignment, and I'm going to use my time today to do some of the time today to make sure you guys know what, well, I'm going to try to make sure, well, I will do my part to make sure you guys know what's going on. And hi, Louisa. Oh, yeah, she's already here. Sorry. Yes. Okay, good. So let's go and actually talk about this, and we'll start our conversation with just a super quick review where we were. And specifically, where we were talking about concave lenses. Concave lenses look something like this. We've got a nice optical axis. We've got our eye of Sauron over here looking at the situation. And we said we can put here's our focal point. Okay, there's the other focal point here. And we'll put our object maybe here. Okay, we did this. We said, following rule 1, parallel light ray goes away from the focal point. That's rule 1. And then rule 2 was if you aim at the other focal point over there, whoa, that's crooked big time. So if you aim at the other focal point, then it goes parallel. There we go. That's rule 2. And we can combine those two into where to find the image by dotting this back. Okay, and here's the image we found. Image, object, right there. That's fine. It's a smaller image. We talked about that. The one thing I did want to point out is that we casually label F here, okay? And we've got a distance to our object. Nice. And we have a distance to our image right there. Now, we already talked about that there's an equation relating those three quantities, distance to the object, distance to the image, and the focal length. And that relationship is the LEnsmaker equation, 1 over di plus 1 over do equals 1 over f. And we use that to find the values for a convex lens to find where the image should form. And we compared it, that was during class when we were still able to go to school. And we did that and worked out pretty well. Now, if this works for convex lenses, that's great. It also works for concave lenses, but we kind of have to make an adjustment. And the adjustment being, obviously, if this distance right here, let's say, is 5 centimeters, yeah, then we have to distinguish what's going on here from what a convex lens is doing, because a convex lens could also have a focal length of 5 centimeters. So what does this mean? Well, it means that because a concave lens does the opposite of focusing. I don't know if that makes any sense. The light kind of gets spread out. Auf Deutsch nennen wir eine Konvexlinse eine Streulinse, a dispersing lens, rather than a Sammellinse. Convex lenses are Sammellinsen that collect light together. So if this lens is doing the opposite, okay, how could we represent that in how we talk about the focal length? If this distance is 5 centimeters, then our focal length should be how much? Bit of a trick question. Put the answer in the chat. The equation will allow us to relate the three quantities di, do, and f, Carly. We'll get back to that in just a minute. But for now, figure out what the focal length is if this distance is 5 centimeters. You were not. Okay, yes. Okay. I think you can get it in a minute when we talk about it a little bit more in detail. But first thing here, the focal length is what? Any clue? Anybody type something in the live stream? Excellent guess. Excellent guess. Excellent guess. Both of those are wrong. Very good. And they're wrong because that will be the correct answer for the convex lens. Good, good. You guys are all guessing the wrong thing, which is perfect. Which is perfect, which is why I'm talking about this. A convex lens that had a distance between the center of the lens and this point as 5 centimeters would have a focal length of 5 centimeters, but this lens does the opposite of a convex lens. How can you represent that in the focal length? If the focal length is not 5 centimeters, I'm going to give you a hint. I'm going to write the 5 centimeters here, and I'm leaving a little space here. What could we put here? There we go, Vicky, you're right. So we put a minus sign in there. A concave lens has a focal length of minus 5 centimeters. Okay, so concave lenses, Streulinsen, have a focal length that's smaller than 0. Okay, for concave, whoa, that is ugly, but good enough. And then for convex lenses, we have f is greater than 0. Okay, concave, f smaller than 0, convex, f is greater than 0. Hi, Johannes. I do not believe we will be good. Yes, it's negative. I don't believe we'll be back on school on the 20th. I think that's unrealistic, but we haven't gotten an official word yet, so we should prepare as if we're returning and not returning at the same time. Okay, I don't know if that makes any sense, but yeah. Okay, Sam, this is your warning, Doodle. Do not, do not, do not, or I'll block you, Doodle. Okay. I don't know when we'll get official word. I would think that would happen soon, but I don't know. The Senate will make that decision, and when they make the decision, they'll announce it, and that could be as late as like the day before school starts until April 19th. And then they say, not doing it. So the situation is fluid, as they're saying. I think we're going to definitely be another couple of weeks at least, but we'll see. Adjust it accordingly based on what we're doing. I have posted an assignment that is due after break. That's the one that's for this optics lab, and based on the assumption that that will be the case, that we will not have in-person school, that we will continue to do what we're doing, and I'm planning on doing these kind of live streams with all my classes after break. That's at least what I'm assuming. And as mentioned before, I don't know if I've mentioned this before. If I haven't mentioned it, I will mention it. I'm going to, in the next couple of weeks, even though it's spring break, I'll still offer one live stream a day. One live stream, well, three live streams a week, I think, 2 or 3 live streams a week for enrichment. And hey, if you're looking for something to do, I'm going to be doing some live streams on astrophysics, how do black holes form, what's the white dwarf, what's a red giant, those kind of things regarding stars. I think it's an interesting topic. It's not part of the curriculum, and it's the time to get together and still learn some physics and learn something, and also give us a little bit of structure. I'll probably schedule those for 11 o'clock, which is late enough that I hope you can get yourself out of bed if you are a late sleeper, but not so late after lunch, then people want to go out for a run or whatever. I figured that'd be a good time. I am still deciding that, Rhea. I am going to do one a day, but my AP Physics class will do probably 2 of those, and then I'll have 2 with this topic, I think, and one I'll just do an open kind of office hour, and I don't know the date yet. I'll do it Monday through Friday. Okay, so Monday through Friday I'll be online. 2 of those will be for AP Physics because they're still preparing for their exams. 2 will be open for anybody just with astrophysics, and 1 will be kind of an open office hour where if you want to come by and ask a question or just chill, I'll do that. Okay, all right, good. So let's come back to this topic here. We have established that concave lenses have a negative focal length. Okay, so that's important. We have also got this equation right here, okay, the LEnsmaker equation that relates the distance to the image, distance to the object, and the focal length. Let's just kind of ballpark this to see if this even works. So we have an example here. We have here, let's say the focal length is a -5. Then it looks to me like the object is about 11 centimeters away. So DO is equal to 11 centimeters. Makes sense? And based on, let's make it actually 10, just to make it a little easier. I'll make it 11, that's fine. So 11 centimeters. And let's see if we can use that information to find DI, okay? So, okay, we got 1 over DI plus 1 over DO. DO is 11, we'll just write that down like that. No units required because Americans are allowed to not include units, in contrast with Germans. Interesting little difference. So and then we divide by -5 over here. Now, there are a couple possibilities. The 2 possibilities being you're good at fractions or you're not good at fractions. And we're assuming everybody's terrible at fractions. So we're going to take this equation and we're going to decimalize it. Okay, so we're going to go 1 over DI plus, and just type that in your calculator, 1 divided by 11. Okay? Type that in and tell me what it is. Just tap it, tap it, tap it, tap it. Put it in the stream. Let's go. Let's go. Sorry, 8th cup of coffee. .09. Very good. And I'm going to take one more digit. I think one more digit is a 1. Is that correct? Yeah, if we take one more digit, it's like 0.09090909. Get it? Oh nine! It's a German joke. Get it? It's funny. It's funny stuff. Okay. All righty. So 0.091 would be the rounding. Okay. And then over here, of course, what's 1 divided by minus 5? 1 divided by minus 5? Do you have the answer? Oh, 9. Thank you. Minus 0.2. Okay. Now let's actually solve that. Very good. Sehr gut, sehr gut, sehr gut. Very good. Okay. So 1 over di is then equal to minus 0.291. Right? I subtracted this from both sides. Good. And then we're going to invert that to find that di is equal to what? Find the answer to flipping this. Flip this. What's the answer for the image distance that we get? Go, go, go. Is anybody doing it? You're supposed to take the inverse of that. Oh, goody. So, Izzy, are you okay with this part right here that I'm boxing, how we got to this part right here? Are we this the way we spell it? I don't even know. Is that okay? Are you okay with this part? Okay. 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 So Izzy says this is okay. Okay. So Gavin said, I'm confused. He doesn't understand. So coming back to our equation, this was 1 over di plus 1 over do equals 1 over f. That's our original LEnsmaker equation. And we remembered to use a negative focal length because this is a concave lens. We plugged those values in, and because we're bad at fractions, we decimalized that, meaning we turned this fraction, which is hard to interpret for normal humans, into a decimal right there, 0.091. And we turned this into a decimal there. Then if we want to put our Arbeitsstrich here, we subtracted 0.091 from both sides. When we subtracted this from both sides, this went away, and we were just left with 1 over di on the left side. And on the right side, we had minus 0.2 minus 0.091, which is equal to minus 0.291. Okay? Now, to find di, we're going to have to take the inverse of this. 1 divided by minus 0.291. Okay, hope that's showing up. Oh, okay. All right, you guys with me? Okay, Izzy's okay? Okay. Okay, So when we take 1 divided by this, if you punch that into your calculator, Rhea posted the answer is minus 3.4. Okay, so that's minus 3.4. And now we left the units off because we won World War II, and we're allowed to do that. But now we put it back in at the final answer. There we go. Okay, so we get minus 3.4 centimeters. There we go. And that's our answer for this, where the image should form. Okay, so a reminder about this. What does this mean? This is a distance, that's easy. But this part is maybe a little bit schnickelig, so you want to make sure you understand that. A negative image distance means that your image is on the left. Oh, crap, doesn't show up. There we go. So our image forms on the left side. That's where our image is, right there. Boop. Okay, and if this is 5 centimeters, this could be about 3.5, so that's fine. So the answer seems pretty reasonable in terms of where we get the image. Okay, I'm going to take a picture of this, and I will post it in our Google Classroom later. For now, though, give me maybe a understanding check. We're going to use the Tiger scale. You guys know what the Tiger scale is? Okay, so the Tiger scale is if you're like a tiger, understanding this, you're just crushing this, then like you give me a 5 response. Don't do it yet. A 5 response for you're a tiger who's totally crushing this, and then it goes down to 4, 3, 2, 1, and 1 would be I'm a zebra about to be eaten by a tiger, and I know that's not the right continent, but just in principle. Okay, so tiger rating is 5. I totally understand this. 1 is I'm a zebra about to be eaten by a tiger. I know that's the wrong continent. And in between would be 2, 3, 4, 5. Okay, so everybody give me a response between 5, tiger, I'm rocking this. 1, I'm a zebra about to be eaten by a tiger. Okay, everybody just type a number in what you're understanding so far about this. Everybody, let's go. 1 through 5. 1 is bad, 5 is good. 1 is bad, 5 is good. Type it in. Keep going. Don't be shy. Okay. 7. Sure. That's nice. Okay, going up to 8. Wow. Very good. Very good. Somebody doesn't understand the scale. Last, I'm going to block you if you don't stop. Okay, good. I've got some good feedback. There were a few 2s in there. Sorry about that. We'll keep working. It's a little mathy. I get that. It's a little tricky, but I hope it'll settle in. And if you have to rewatch this, that's a nice thing. It's posted on YouTube afterwards, and I'll also post this picture. I hope that you can get it afterwards, even if you had a little bit of trouble. And then also at another time, if you still have trouble, I'll be happy to answer a question about it. But let's take a picture for now. Oh, okay. Okay, So I will spend a couple more minutes explaining this with the -5 first of all, and then we'll get back to the -3.4 in just a second. Okay. So and what I'm going to do is I'm going to show you two pictures. Okay, so we have two different lenses here. Okay, two different lenses. We have a convex lens, Sammellinse, and we have a concave lens. Okay, and in both cases, if we were to just measure this distance, we would find that this distance is 5 centimeters, and this distance is 5 centimeters. Okay, both these lenses have these distances as 5 centimeters. Well, they do two different things, so they have to somehow have different focal lengths. Okay, and the idea is that we consider the focal length of a convex lens, which actually does focus light. And what I mean by that is we take parallel light, right? We said that light that's parallel to the axis here is focused there. It is focusing. It has a positive focal length. We will call F equals plus 5 centimeters then for a convex lens. But for a concave lens, it does the opposite. It takes this light ray, sends it out that way, sends it out that way, and then light down here goes this way. There we go. So this does the opposite of focusing, really, right? It doesn't focus at the focal length. It shoots it away as if it's coming from the focal length. Therefore, we will say F is equal to minus 5 centimeters. It does the opposite of what a convex lens does, and where that -5 and +5 comes from. Hi, Lena. Okay, there we go. I hope that makes more sense with the -5. Becky said she understood the -3.4, so I think we're okay then, generally. And again, I'll save this as well, and then if you have questions still about this, you can get that. This is concave over here, and this is convex. So we're all good. Okay, so in the lab will allow you to actually generate these kind of diagrams using a lens that you can digitally manipulate, which is pretty cool. So you get you go in the program. Wow, that's not drawn well. So that's not drawn well either. Ignore that. Hang on, I'm going to do a better job on that. There we go. That's pretty. Okay, good. So we have a nice convex lens. And what you can do, you can manipulate the lens in terms of changing its curvature radius and how tall it is. And I think you can also manipulate its refractive index, like if it's made of glass or plastic, and see what happens when you change those things. Now, there are disadvantages to doing an online lab, and there are advantages. And this is an advantage because if I gave you an actual glass or plastic lens in the physics lab, you couldn't be like, oh, I wonder what happens if we change the radius of curvature like this, or like make it taller or something, because you only have one lens or 3 lenses or 5 lenses. And here you have a whole range of lenses that you can look at. You can play around with that a little bit, and I hope it's fun. I think it's fun, but my sense of fun is maybe weird. But if you play around with that, you can try it out. Once you have a lens you like, I don't know, you can then do the experiment. Okay, and here's the idea of the experiment. So we have this lens, and of course there's a focal point. Let's say it's here, and then the other focal point's over here. Boop, boop. Okay, and what we're going to do is we're going to try for different objects that are further away than the focal point. Here we go. So let's put one over here. Okay. Here's a red object. We're going to find where the image forms. We could do this in the lab. So we would have some kind of arrow shining or a candle or something like that. And then we would have over here a screen to actually see where we would get a focused image. So this is something we can do in the lab. We'd have to darken the room and all that stuff, but we would do this. Okay, so let's imagine we do this. And let's see where this image forms. Now, if you get the light ray coming in through here, you would, of course, then get this thing going this way. If this thing comes through the focal point, imagine it's through the focal point there, it would go parallel. There you go. And we form the image here. Here's object, and here's image. Okay, and we did that to find how the image forms. Okay, all set. We've got where that image forms, and we can find the image distance, right? This would be DI. This would be DO. Okay? And we would now have our first data point. For our data table. Okay, hey, this looks a little bit pretty much like a lab report now, right? Remember, because this picture would be our setup, right? Setup. Okay, and now we're doing the data table. Okay, good. We're getting okay, this is making sense to me. So now we've got our first data point that we can write down. If we imagine this is 5, we said F is 5. And let's see, 5, 10, like 12 centimeters would be the first one here. And then over here we would get maybe like 10 or something. I'm not sure. Okay, good. And now we'd vary the object distance closer and further away to get at least 4 or 5 different measurements. So let's put another arrow in here. I'm going to put a different color in to make sure you understand how to get this. So we're going to put this one right here. Okay. Here's the blue one. Let's actually, yeah, that's fine. So here's our parallel array. Whoop. And we're going to direct it through here. Okay, sweet. Here's rule 1. And we're going to do rule 2. Oh, jeez. All right, kind of ballparking a little bit here. There's our second arrow. Here's our second image. So we have a red object forming a red image, and we have a blue object forming a blue image. Okay, so let's take a look. Okay, here's blue DO, and in our case, this was 5, like maybe 8 centimeters or something like that would be DO. And then over here, this was 5, 10, 11 or something like that. Okay? All right, now I just ballparked this. In your actual lab, you would use a ruler, a digital ruler. So you can have a ruler that you can move back and forth in the lab and you can make these measurements. So far, these measurements are very imprecise, but assuming so do you understand how we would get these values and how to do this? Does this make sense? Give me a yes or no if this makes sense. Y or N, please. You guys still there? Yeah, okay, yes, good, makes sense. I hope it makes sense. Kinda, okay, not making sense, okay. Okay? All right? Okay. So you can move with your mouse this object. You'll have an actual virtual arrow that you can move back and forth. And I want you guys to, for several positions, maybe about 5 different positions, you'll measure how far from the lens it is, and you'll use a virtual ruler to actually make that measurement. So kind of like this, you kind of measure the position, how far it's over with your virtual ruler to find how far away it is. You'll also measure the distance to the image, and you'll write down those 2 values in your table as the object distance and the image distance. You will then repeat that with a second one. I've made it blue to distinguish it from the red one. And then for the blue one, you also get 2 values. And now we could do a green one and a purple one and, orange, but it's going to get very cluttered. So I'm not going to do that. But you should get those measurements, and there should be a table with DOs and DIs that are different values because you're varying the object distance. Okay? Now, let's scooch along. I'm going to move this down a little bit to actually talk about now how we're going to analyze this data. I know we're a little tight for time. I think we can do this. So sorry it's taking a little longer. So specifically, we have now, and now if you're a German, you might have been sensitive to me leaving room here. We're going to leave 2 different columns at the end here for something we need to calculate. Because when we look at the equation we have, right? The equation we have is 1 over di plus 1 over do equals 1 over f. Okay, that's the equation. It's not an equation that involves do and di. So what we're going to do is we're going to calculate those values, 1 divided by do and 1 divided by di. Okay? Make sense? Hi, Emma. So we're going to calculate those values, 1 over do and 1 over di, and then we're going to manipulate those and analyze the data. It's due after break, so it's actually, I'm just talking about it, but it's going to be like April 24th or something. So it's quite a while away, so it's at least not due for another 3 weeks. Okay? So let's take a look. We have now this equation. Okay? Now watch this, famous last words of skateboarders everywhere. I'm going to manipulate it by taking 1 over do and subtracting it from both sides. So I've rewritten this equation by moving the 1 over do to the right side. And of course, to do that, I have to subtract it. The other thing I did, which might be a bit surprising to you, is I wrote this kind of weird. I wrote this as minus 1 times 1 over do rather than just minus 1 over do. And there's a good reason for that. Okay? And I'll explain that to you. What we're going to do is we're going to consider this 1 over do our x variable. Sorry, x variable. And we're going to consider 1 over di our y variable. Okay? So we're going to make a graph where we plot 1 divided by di on this axis and 1 divided by do on this axis. Okay? So let's take a look at what we have here. do is 12. This will be 1 over 12. di is 10. This would be 1 over 10. This is 1 over do, so it's 1 divided by 8. And this value over here would be 1 over 11. You need to calculate these based on the first 2 columns. Columns 3 and 4, you calculate based on columns 1 and 2. Make sense? I hope. Okay. Now, the data you'll get will look like this. Okay? I'll just give you that. It'll look like that. And you'll be like, why? Well, it'll look like that because if you look at our equation, okay, we're going to now go underneath here and say, okay, well, this is our y variable, right? 1 over di is y. We still have minus 1. 1 over do is our x variable. And then we have here b. Ah, shit, I gave it away. Okay. Okay. What I meant to write here is this, m. There we go. Y equals mx plus b. That's the way we talk about straight lines generally, right? Our y variable is 1 over di. Our x variable is 1 over do. Well, if we plot it, therefore, we would expect that we get a slope of what? What is the slope that we're expecting? So slope is this value right here, right? The value in front of the x. Type in the chat the value for the slope. Right. Correct. Good job, Izzy. Brilliant. I had already written the answer. So the slope should be minus 1, exactly. And then, of course, our y-intercept should be what? Okay. What should be our y-intercept in this situation? Type it in the chat. The y-intercept should be good. 1 over f, exactly. There it is. So that means if you guys make this graph and you find the y-intercept, then that y-intercept should be the correct value for 1 divided by f. So not 5, watch out, should be 0.2, right? Because 1 divided by 5 should be 0.2. Both this value right here and this value right here, by the way, the x and y-intercept should be the same. They should both be 1 divided by f or 0.2 about. So this will allow you to find a value, a measured value for the focal length. And specifically, your measured value for the focal length, measured, is equal to 1 divided by the y-intercept. Your measured value for the focal length is 1 divided by the is 1 divided by the y-intercept. That's your measured value, and you can compare that with the value that the computer program tells you is the focal length of that lens. Okay? That's the general idea. We're out of time. I hope this helps you along with the lab activity. We discussed basically everything here. You've got your graph. That's part 3. Here's the analysis. You put a straight line through it. You find B, yada, yada. take a look at this review, and then if you have questions, we can talk about it after break, okay? Or you can email me as well, okay? Have a good break, you guys, and I'll be around by email, live stream. I'll send the schedule out and talk to you guys soon. Bye-bye.